It's easy to do. So anyway, we just have our number of observations is twice our number of data values because we have x and y displacements. And then we just reshape our Green's functions, make this nice, well, here I call it A matrix, but it's actually a G matrix. And then we create this diagonal matrix, which is going to be our penalty function. And then we concatenate our actual data with our a priori data, which is zeros, or our a priori solution values, which are zeros. And the number of inversions will perform just the NumPy has this, when you create an array, it has different attributes. One of them is shape, which is just the dimensions of the array. And so we're saying that the number of inversions we're performing is the shape of that penalty, those values that we read. So we're going to make a bunch of empty arrays to hold our results. And we're going to fill the first part with the coordinates. And then we're just going to loop over our inversions. So then we have penalty value. The penalty matrix is just that particular value for this inversion multiplied by that diagonal matrix. And then we stack that, our Green's functions, and this diagonal matrix. So then we just form, this is the generalized inverse that I showed you. That's what this is doing right here. And then, so our solution is just, in NumPy, this is considered a dot product multiplying the matrix times our data vector. And then we get our solution, and then we, from there we also, so we compute our predicted data values, and then compare that to the actual solution and get a norm. So we loop over all of our things and do that. And that's pretty much that. So we can, we'll run that. Let me get this. Okay. What this should say, there's this a typo. It should say flip.py. I usually make these executable so you don't have to this one right here. This is the Python script we've just been looking at right here, and it's one level up. It's in the Green's functions directory. It's invertslip.py, and the reason is because we use it for both the reverse fault and the problems, so no sense writing it twice. And so then this is what happened when we ran it. And you see, as you increase your penalty parameter, your fit to the data is not as good because you made it you tried to force your solution to be just to look and see what these results look like is just a simple plotting script, which we can look at. It's very, what's my time? Let's not look at that. Let's just run it. Okay. Let me just, So what I'll do, okay, so all that did, black is what our input model was. That was our solution. And so all you see, this is, like I said, a very stupid inversion. And you penalized it, like the more you penalize it, the more it wants to go to 0. So this is the highest penalty parameter there. And then as you decrease the penalty parameter, you get closer and closer to this solution. You're still getting kind of jagged here, so it's not completely resolved. But what you would, in reality, and I believe I have this in the README as exercises for the reader. Well, okay, change the material properties. This could be for the forward and model and for the Green's functions. Change the slip distribution. Move or increase or decrease the number of observations. Increase or decrease the resolution of the mesh to see if that makes a difference. Try different penalty functions. For instance, a simple 1D Laplacian, which is just a 1 minus 2, 1 kind of pattern running down the diagonal. Also, adding noise. There's numpy.random package that allows you to generate all sorts of distributions. So you could do that for your noise. Yeah, so I think, yeah, playing with this sort of thing, I believe you could end up with something much more interesting. But this is a demonstration, and then, so this is 2D. Extending it to 3D would not be really that much of a task. You're still just generating your Green's functions and doing the same sort of inversion. Just have 3 components instead of 2. So there's that. I think, should I do the quick 3D? I can just, let me quit out of this. Okay, maybe questions are better, yes. Okay, questions? The 3D one's pretty basic, so I don't think we need to do it. Yes?
When you're describing the speed back translated components in the global components or the local striking and the corrections.
The slip that you apply?
Yeah.
No, that'll be the slip that you apply is in the local coordinates. So you'll say how much in 3D you would say how much left lateral, how much reverse slip. Yeah. Yes, yes. Yeah, because the fault within Pilot we have all of the orientation information for each vertex on the fault. So yeah. Yes. Does the you mean for the finite element solution? I don't know if we output that anywhere. So, oh, you mean which one corresponds to what point in like a global vector? I think, okay, you're talking about throughout the whole mesh. Well, we don't, I think if you're asking what I think you're asking, I think we just, you know the coordinates at each point, and you know the solution vector at that point. So is that what you mean? That, well, we can get the field at any vertex. Yeah, yeah.
Evaluate the field at any point, but the field is just a set of coefficients for basis functions. When you evaluate it at a point, you just sum up the contribution of each one of those functions with that weight. So
yeah, it depends if it's, yeah.
Those coefficients with the mesh, we have the mesh in the same file and the ordering of the node.
It's the same. Yeah. 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 I think it's more of a bookkeeping thing than a, yes. You can put that in, yes. We didn't for this one, but okay, there's another exercise for the user. You could take the 2D subduction zone example we had this morning, which has a small amount of topography in it, and you could do the same thing. I don't think for that particular problem, I don't think it will make any difference, but you can, where I think, well, okay, if you're doing a subduction zone, bathymetry will matter if you get like really, where the fault's really shallow. So, yeah, so you can certainly put that in. Yeah. Okay, yeah. Wait, say, what was that?
So if you're asking if I want my mesh to honor a specific topology for the fault surface, like the nodes of my mesh to correspond to specific points on a fault surface. That's the mesh generator, and generally we don't.
Yeah.
We don't do that. We say, I want a mesh at such and such a resolution.
Yeah.
So if you have if you wanted to then extract information at particular locations and from your output, then you would have to get all of the fault output and then interpolate.
Yeah. I think, are you thinking in terms of where you apply impulses? Yeah, I think in that case, you're better off doing a nice discretization, and then you can, like, for instance, if you want to do like macro Green's functions, you can combine them to a particular location, integrate them to get the response at a, is that the kind of thing you're talking about? Or, yeah, yeah. Okay. People are tired now?